So, hey, thank you for the introduction. Also, first of all, allow me to thank you, to thank the organizers for all this wonderful conference. We have a wonderful venue, and also there are people from all sorts of backgrounds. So it's a real pleasure. I've been learning a lot already today in the talks. So what I will be talking about is actually kind of a project we're getting started. So with this people, so Pierre Bielawski himself, there's Valentin who is here as well, Guillaume here as well, and also we have a larger working group. So I will be talking about this topic of thermodynamics of Lie groups, which has been touched upon in the previous talks. And in particular, I will give some specific examples. So before that, I'm going to give some give some definitions which have already been given to some extent in the previous talks. So, right, okay. So I said thermodynamics, but actually it would be maybe more precise to talk about statistical mechanics, and actually statistical mechanics at equilibrium for the present work. So let's say, I'm not being precise here, so we have a mechanical system with state space M. There is an energy function with real values. We want to describe a statistical state by a probability distribution on M. And so we are looking for to describe equilibrium states. So let's say we have a given energy, and the system is isolated, and we'll let it relax to an equilibrium state, so it will maximize its entropy. And this equilibrium state will be described by a probability distribution, which maximizes this entropy at a given energy. So it looks something like this, which you've probably already seen earlier today or probably earlier. So yes. So there is a normalization factor here, and it is dependent on the point and on the point of the state space, and especially on its energy. And you notice here there is a parameter beta, which is in a thermodynamical context identified with the inverse temperature. This will be important later. Okay, so that's something pretty standard. So it's called the Boltzmann distribution, and in generalized cases it will be called the Gibbs distribution. So this is a pretty standard, quite old, and we want to, this has to be coupled with the framework of geometrical mechanics. So now let's say M has a symplectic form. We're getting into this geometrical context we're familiar with. So it also has Poisson bivector, and there is the action of a symmetry Lie group, which I call G. So now, what was the energy generalized by a momentum map? It doesn't have value in R, but in the more general dual of the algebra of G. So I will only talk about what's called strong momentum map. So everything is already equivariant on the nose. There's no need to deal with a cocycle for simplicity here. Okay, so this we want to, how does it relate to this energy thing? Well, of course, in the case of time translation, so we have the dual of R as the Lie algebra, and we have the corresponding momentum map is the energy, and it generalizes to, well, linear momentum and angular momentum. I don't need to go into more details about this. So how does it fit with what I said earlier about the Gibbs distribution? So now we want to replace the energy with the momentum map, and we are looking for a probability distribution which maximizes entropy under fixed expectation value for this momentum. So we obtain basically the same thing, except that now, since mu takes value in the dual of a Lie algebra, beta has to take value, well, in the Lie algebra itself. And here it is important to work with beta and not the temperature. So it is called generalized temperature. It was called geometrical temperature earlier in an earlier talk, or it can be called generalized inverse temperature or coldness. But we see that working with the inverse temperature allows us to keep this structure of Lie algebra intact. So we have all this very rich geometry, which is intact. And here we have this normalization factor, which is pretty much the same. Here I'm using this notation for the Liouville measure, since now M is a symplectic manifold. So now let me say a few words about this Z factor. So of course, for this to be well defined, this has to converge. This is an integrability condition which is non-trivial. So in the case of only energy, typically related to the usual requirement that the energy has a lower bound so that the system can reach a stable equilibrium. So this motivates the definition, which won't be new today, the set of generalized temperature of the Gibbs set. It will be the largest open subset of the Lie algebra, G, on which this converges, as well as its higher differentials. And we want it to be an open subset, so we'll require that this converge on a neighborhood of beta. Right. So in particular, we'll be interested in geometry. I will say in the next slide what I mean by its geometry, but to begin with, it is stable under the adjoint action of G. So what is its geometry? So now let's say we have any Hamiltonian symplectic G manifold M. So we can define this omega, this set of generalized temperatures. And so what can we define from this structure on omega? Well, we can define the expected momentum. So given any point in omega, we have a probability distribution on M. So for example, this allows us to define the expected momentum, which is a value of G star. It can also be seen as a one-form on omega, since it depends on the point of omega and takes value in the dual of this G as vector space. And we'll be also interested in what's called the Fischer-Rao metric, or can also be sometimes called, Frédéric likes to call it the Fischer-Rao-Souriau metric, because it was also discovered by Souriau in this framework, which is an element of G star tensored with itself. So it is the expectation value of mu time tensored with itself. And it can also be seen as a metric, actually. So it's positive, it turns out to be positive. If we identify the cotangent here with G star, then it can be seen as a metric. And the two of these are equivariant, or invariant, depending on how you see them. And we will be interested in this geometry here. All right, so let me just give you a quick example, or maybe illustration of this integrability condition. It is non-trivial. In particular, Souriau, in his book Structure of Dynamical Systems, he proved that an isolated system cannot have equilibrium states for the Galilean group or the Poincare group. So what I'm saying, it's calling here equilibrium states, I mean, it cannot have generalized temperatures. So we have to be careful about the groups we are dealing with. And if you think a bit about it, it makes sense. If you, for example, you consider a gas, a perfect gas in a vacuum without boundaries or anything, it won't reach an equilibrium with a homogeneous density which is non-zero. Or you can have an intuition about why this can't happen. So there are cohomological reasons for that. So I think I will skip then this this discussion. Let me give you some more elements of examples for this generalized temperature and generalized equilibrium, this notion of equilibrium. So another example that Souriau gives in his book is the case of a perfect gas in a centrifuge. Oh, there should be a minus sign here. So to begin with, what do we expect as an equilibrium state? So we have a centrifuge, so it's rotating, it has walls, it is in a confined volume, and inside there is a gas, a perfect gas. So we don't consider internal interactions. So at equilibrium, the gas needs to have the same temperature as the centrifuge, so there is a thermal equilibrium, but there should also be a kind of angular velocity equilibrium. So that's what this generalized temperature means. So we have a generalized thermal equilibrium, which takes into account this rotation. And so the generalized temperature will be an element, so I write it as an element of the Galilean Lie algebra, but of course we want to consider a Seb algebra of this, because we know that we can't have, for an isolated system, generalized temperature for the whole Galilean Lie algebra. So I just write it. So we have a generalized generator of time translations here. So this corresponds to energy and temperature. And we have a generator of rotations here. And so, this is how you interpret this larger generalized temperature, which do not only live into time translation, but in larger Lie algebra. So we can compute probabilities of presence, but this won't be very relevant for this talk. Let me, I guess, skip this second example as well. So now I'm moving into our actual work, what is inside of paper. I won't give lots of complex computations, so you will find the details in the proceedings. So what we did is we're trying to look for these omegas. So I told you that these omegas are not always non-empty. So we are looking for some non-empty omegas, and we are looking to investigate their structure, especially their Riemannian structure. So how do we found this omega? Well, we have found a family of these omegas which are minimal nilpotent, well, co-adjoint orbits. Let me define what is a minimal nilpotent adjoint orbit to begin with. So let's say we have G, which is a simple real Lie group. So I have a Nielsen decomposition of this Lie group. And the compact group, an abelian group, and here we have a nilpotent Lie group. So this A abelian group, it acts on the Lie algebra of G in a diagonalizable fashion. So we have a set of restricted roots. So we'll look for a maximal positive restricted roots, and we'll look for a root vector associated with this maximal positive restricted roots. So by definition, this subgroup N will have a trivial adjoint action on E because alpha is maximal, and this the subgroup A will have very simple adjoint action on E. It will only act by positive real scalars. So we have very simple adjoint action of at least this part of the group. So for this reason, actually the orbit is quite simple, and it can be proven to be, in a sense, minimal among nilpotent adjoint orbits. So we will look at the dual, the corresponding adjoint orbits. So since G has a simple Lie group, it is semi-simple, so we have the Killing form, which identifies G with its dual in an equivariant fashion. So now we can consider the image of our minimal nilpotent adjoint orbit under the Killing form. It will be the minimal nilpotent co-adjoint orbit. So as a sub-manifold of G star, there is, well, a tautological embedding, so it will act as a momentum map. This is a map from our orbit to G star. And also it has a symplectic structure because it is an co-adjoint orbit. So this O is an Hamiltonian symplectic G manifold. And our theorem, which is in our paper, is that let's consider the center of our K group. So we have this K group here. It has a Lie algebra, which I write fractal K. And let's consider the center of this Lie algebra. And let's consider only half of this, so only the vector which has a positive Killing product with our E vector. I recall this is the root vector we are considering. Then in this case, Z belongs to the set of generalized temperatures. So that means that the integrability condition is respect. And not only on Z, but on a neighborhood of Z. And I should say maybe on the neighborhood of the orbit of Z, because omega is stable under the adjoint action. In particular, we have a family of Lie group. Well, I give some example. We have some families of Lie group for which this is verified. So for example, if you consider these Lie groups, and actually, also sometimes you have to be careful about which K you consider, but this is suggested by notation here. So we have a family of Lie groups for which these omegas are non-empty. So of course the question now is what's their thermodynamical geometry? So I will give an illustration with an elementary example. So let's look at basically the simplest example we can have in mind. So SL2 of R. So here is how it decomposes, very simple. And so we are interested in the nilpotent orbits. So since we have this Killing metric, we can identify, of course, the Lie algebra in its dual. So we don't have to be very careful about this. So the adjoint orbits are the connected components of the pseudosphere for all the Killing metric, which is of Lorentzian type. In particular, the nilpotent orbits are the half light cones of this Killing metric. And if we look at their sets of generalized temperature, so actually this was Charles-Michel Mal in the paper 2020 looked into it, but actually there was something missing in his analysis, and it's Guillaume who noticed that actually who found these sets of generalized temperatures. So these are non-empty, of course, and these are the opposite time-like cones, the opposite cones of time-like vector, opposite to these light cones. So now we have these time cones, and we want to understand their thermodynamical geometry. And here is, their geometry is, as expected, is very simple, because we have a very symmetric, very simple case. So the Fischer-Rao metric on each of these is isometric to a direct product between the Euclidean line and the hyperbolic plane. So if we are interested in this, sorry, I have some conflicting notation. This is the normalization factor of this Z is the normalization factor. So it can be identified as the exponential of these Euclidean line components. And if we are interested in the expected momentum as a one form, as I said, it takes value in the dual of the the dual of the Lie algebra, but it can be seen as a one form, and as a one form, it's only minus the differential of this Z, the R component, the Euclidean line component of our cone of sets of generalized temperature. So that's actually, I guess I'm a bit early. That's what I wanted to say about our paper. So just a very few references. So we will find a more complete list of reference in our paper at the end of the paper. So only the few references I talked about during the talk. And that will be it. So thank you for your attention.
Thank you very much for this nice talk. Is there any question or comment?
But as an exceptional group which satisfies this condition, exceptional.
Yes.
Can you give a list? What are exceptional group?
So
G2 or?
So okay. So I didn't write them. Sorry. So the question, okay, what the answer I can give to your question is these exceptional groups which are associated. So I don't know my geometry of exceptional Lie groups. I think it's.
I think G2. No.
I don't think
G2,
G2, but E. Yes, right.
No G2.
But you have okay. So you have the symmetric Hermitian spaces.
This is completely.
No, this is not complete.
No,
This is not complete. This is not complete. So you have the.
Many real form for the same.
As soon as you have G, simple, absolutely simple, with maximal compact K, with non-discrete center, then you are.
So.
Maximal compact subgroup must have center.
Non-discrete center.
No, but then it is means homogeneous.
G over K. G over K.
Taylor symmetric space.
Yes.
Exactly.
Then of course it's no.
Yes.
Exactly Hermitian symmetric space.
Yes. So that's what we. Yes. Exactly.
Mm-hmm.
So I didn't give the exceptional ones.
Just examples.
That's not a complete list. No. Just to give some list. Thank you for the question. Yes.
Just to ask you, you consider the case where the orbit is minimal.
Yes.
And can you tell me which specific property of that orbit you use to prove your theorem? Is your theorem is correct for any nilpotent orbit or only for minimal orbit?
So the way we prove it is that we have. So I gave an explicit expression for this. So actually, we lead actual computations, and we can go further computations.
Okay.
And since the orbit is minimal, yes. So we have very simple form for the orbits because we are here. This is here. That's the fact that the orbit is minimal is important for us. We have no we have trivial adjoint action of this n. And when it is non-trivial, things get a bit much more complicated. I tried to do the computations, and I don't have as simple expressions for the normalization factor.
I understand.
So right,
That's
because
okay.
if you
But it could be interesting to try
Yes,
to,
yes,
to,
I
to
tried-
do the job for the other orbits.
at least the next one, right?
Yeah,
The
okay.
next one would be interesting to have more examples.
Okay.
Yes, thank you.
Thank you. Is there any other question or comment? If not, let's thank the speaker again.